push to the right at 42. That's the max that the static can do for all the forces. So A, how large is the force of friction? It would be 42. It'd be matching us. Well, I guess they've worded it kind of strangely because their first sentence is a force of 42 is needed to start a box sliding across the floor. Usually what that means is that that's the max, so anything after that, but that usually would mean that when you are at 42, you're still technically in the static case because that's what friction can do. So I'd say that this is still the static case because you're at the very last point. Anything, even a slight breath of air would get it to start moving after that. So it would be static. What is the coefficient of friction? So for that, we're going to come to this formula. It goes like this, that the force of friction is equal to the coefficient of friction, mu. That's like a percentage. And that gets multiplied by the normal force. So whatever the normal force is, gets a percentage of that is the frictional force. So we would say 42 is the frictional force. That is equal to an unknown coefficient of friction times 55, which is the normal force. So mu should just tell us what percentage of 55 is 42. So all you got to do is divide both sides. This is your main equation here for the friction. Divide by 55 on both sides. Cancels on the right. So mu is whatever this is. Does anybody able to do that on a calculator? Or?
It's 0.7636.
Okay, 0.7636. I'll just call it 0.76, let's say. All right, so that's your coefficient of friction. All from this equation. This is going to work for static and kinetic. Just what exactly it means is just different in those two cases. In the kinetic, it does give you the force of friction. In the static, it just tells you the max friction that the thing can take. All right, so that's the first one. Any questions about that problem? Seem okay? Good, good, good. All right. I'm going to try the, oops, I always do that. All right, so the one is done. Good. Okay. 2, now they give us the coefficient of friction. They say that that's the coefficient of kinetic friction, kinetic, between the crate and the floor. How much force is needed to slide a 92 kilogram crate uniformly across the floor? So they didn't tell us the weight. They told us the mass. And they gave us the coefficient, but they want the amount of force. And to get it to go uniformly, we would need a situation kind of like this where they're in balance. And then it won't slow down or speed up. It'll just go at a constant speed. So I'll remake this for the next one. I guess we'll get rid of what we just did. And I think this should all be good, except the numbers will be different. So this is a 92 kilogram case. should have labeled my newtons before. We know it's mu is 0.2. Oh, 0.2, 20%. And I think that's it. They just want to know, is that it? Let me check. Yeah, so they want to know how much force will keep it going uniformly. All right, so these are not 55. We have to figure out what they are. It'll be from the weight equation. F equals mass times the acceleration due to gravity. That we usually use 9.8. So 92 times 9.8. Anybody have that? If you want to just go easy on yourself.
I was gonna say it's 901.6.
Okay. You can sort of go easier on yourself and just say, oh, G is about 10. So we'll just make that 920. But it's not quite 10. It's actually 9.8. It's 901 or 910?
901.
Okay. All right, so that's the weight of it. So the newtons downward would be 90, I'll round to 902. And then that will be 902 for the normal force because it's not going into the ground. So we know that the normal force times the kinetic coefficient, which was 0.2, will give us the frictional force that we need. So try to take 20% of 902. Can we do 0.2 times 902?
180.4.
Okay, thank you. 180. I'll just leave it at 180 newtons. So we would need to push it 180 newtons in order to balance the 180 newtons. That is the the kinetic friction. Should pop up. There he is. Welcome. We're working on one of the worksheets on Canvas right now. The last one that I posted, I think. So the kinetic friction will be able to put up with 180 newtons worth of force for a 92 kilogram object. The 92 kilogram object has a weight of 902 newtons, and 20% of that is what the friction can do. So we would have to balance that in order to keep it in equilibrium, to keep it from speeding up or slowing down. So that would be number 2. It's just 180 pretty much. Are you guys good with that? Good. So we're just using F equals ma again. And this new one, little friction force equals mu times the normal force. All right, for 3, This one's, I guess, is a conceptual one. Why is it more difficult to lean over and push a heavy box across the floor than it is to attach a rope and pull the box at the same angle? So you sort of have this bit of a downward angle at the box. Why is it harder to push the box than it is to pull the box? And they want us to draw a force diagram for each situation and turn the vector, the force vector, into its component parts, where there's a vertical part and a horizontal part. And then they want us to think about the normal force. Any ideas before we start that one? Why would it be harder to push the box? You can switch your tab if mine was showing. And than it is to pull the box. If you want to sketch how the force might work, go ahead and think for a second.
What does it mean by lean over?
So like, imagine you're sliding a desk over like a heavy desk across the floor. If you're pushing on it and you're kind of taller than it, I think it just means that you're like pushing, you're leaning down into, yeah, like, can you see me? Like you're pushing, where are my hands? Like down, like you're sort of pushing it, as opposed to like pulling it at the same angle.
Probably because you're applying pressure when you're pushing downward instead of just pulling across.
Pressure on what do you mean?
Like you're adding more force to the ground, towards the ground.
Yeah. Good. Yeah. Very good. That was it, pretty much. Whereas if you're lifting it, you're kind of alleviating that pressure on the floor. Yeah. So where am I? All right. So here is. I'll make a new picture, I guess. I'll get rid of all the numbers now. All right, so it is not one of these straight across forces. It's not quite as perfect as a model. We either have maybe a force like this, sort of getting pushed onto the box, or we could have a force like this, where you're pulling on the box. Same angle. But in one case, if you think of that box